So in chapter 10, we've dealt with parametric equations. We transitioned into talking about polar coordinates in calculus with polar coordinates. We've done, in the last section, we did conic sections. And finally in 10.6, what we're going to tackle is conic sections in polar coordinates. Okay, so kind of combining all the things we've talked about so far. So conic sections in polar coordinates. So there's really two kind of ways to think about this, and I want to describe the result, and then we'll kind of see how this plays out. And so I'm just going to call this a theorem. And this is a theorem. So on that handout that I have on Canvas, this theorem is plainly written there. But even though it's there, I'm just going to write it again. I'm going to let F be a point called the focus. Okay, so F is a point called the focus. Oh, I'm going to let L be a line called the directrix. And then given a point F and given a line L, the set of points, so the set of points P, such that the distance between the focus and the points P divided by the distance between the points P and the line, the directrix L, is some constant E, okay, where E is some constant greater than or equal to 0. This is going to be a conic section. So this is a conic section, okay? E is the number here that's going to be called the eccentricity. Okay, so here, this number E is not the 2.7 Euler's number that we're used to. E is just used because this is the eccentricity. So here E is the eccentricity of the curve. So of the conic section. And it turns out that if E is equal to 0, the conic section that we get is a circle. I'll explain the E equals 0 is a little bit of a strange thing to talk about here, because it turns out what has to happen when you talk about an eccentricity of 0 is that your directrix is actually a line at infinity, which is a little bit strange, but it turns out that's the right way to think about this. We don't have to think about that part too hard. If E is 0, we get a circle. If E is positive but less than 1, okay, it turns out that we get an ellipse. If E is equal to 1, then think about what that says. The ratio of the distance between, well, in other words, the distance between the focus and the directrix is equal. That's exactly what we get when we have a parabola. And if E is greater than 1, then we get a hyperbola. Okay, and so this is really the basic stuff to know about conics and polar coordinates. It turns out that all conics and polar coordinates are going to look like ED over 1 plus E cosine theta, or ED over 1 minus E cosine theta. I'll show you what these graphs are going to look like in a second. Or R equals ED over 1 plus or minus E sine theta. Okay, and so that's going to be the basic form that all of these are going to take. And you're going to be given some kind of polar graph, and then given that polar, you're going to be given some equation, and then you're going to have to come up with on your own what are the values of E and D, and therefore, identify the conic. Is it an ellipse, a parabola, a hyperbola? What's the directrix? How does it look? And so here's the general situation. If you have R equals ED over 1 plus cosine theta, it turns out that that's going to be centered on the x-axis. My pen doesn't want to work here. Okay, this is going to be centered on the x-axis. And so this is going to have some shape like that. And the shape exact is going to depend on whether it's an ellipse, a parabola, or a hyperbola. And then the directrix is going to be x equals d. Okay, so that's r equals ed over 1 plus e cosine theta. If it's r equals ed over 1 minus e cosine theta, well, we know how to deal with that. We just are going to flip this so that the conic section opens to the right. And then there's the focus F. So here, these curves, I should just mention that these curves all have a focus of the origin, 0, 0 in Cartesian coordinates. And then the directrix is going to be whatever this line is. We'll figure it out in a second. Okay, so here the directrix would be x equals minus d. So it's just a reflection over the y-axis. And then if you replace cosine with sine, then these open up and down. It makes reasonable sense given that sine involves the y-coordinate. So you get r equals ed over 1 plus e sine theta. R equals ed over 1 minus e sine theta. These are going to be similar. The 1 plus e sine theta is actually going to open down. So it's going to look like that with a positive directrix, y equals d. And 1 minus e sine theta is going to open up with a negative directrix. So the way I like to remember these formulas is I like to think of the sign here. So this plus or this minus is telling me whether the directrix is going to be positive or negative. So if it's plus, then the directrix is positive. Likewise with sine, if it's plus, then the directrix is positive. And if the sign is negative, then the directrix is negative. And likewise for the cosine term. Okay, and that's how I kind of keep all these things straight. So when you're graphing these, that's what it's going to look like. Of course, the exact shape is going to depend on whether it's a parabola, an ellipse, or a hyperbola. Okay. So there's really two kind of loose ends that I want to tie up here. The first is, why is this equation the right thing to talk about when we're doing conics and polar coordinates? And so let's start with thinking about the polar coordinates. They're thinking about the conic sections that we've talked about so far. And it turns out that conic sections are all going to look like something like ax squared plus bx plus cy squared plus dy equals e, something like that. And that's the right thing to look at when we're talking about conics, because, for example, if a and c have the same sign, so if they're both positive or both negative, we get an ellipse, because we're going to have like a x squared plus y squared on one side, and they'll be scaled, of course, so that's why it's in general an ellipse. Of course, if a and c are actually equal to each other, then you get a circle. And you can complete the square to figure out the other parts. It doesn't matter. If a and c have opposite signs, so if one's positive and one's negative, you get a hyperbola. And if exactly one of a or c is 0, then you get a parabola. They can't both be 0, of course, because then you just get a line. We're not talking about conic sections anymore. You have a first degree polynomial, not a second degree polynomial. But anyways, all conic sections look like this. So that's just kind of the first thing to keep in mind. And then if we look at, I'm just going to pick one of these equations. So something like r equals ed over 1 plus e cosine theta. And what I want to do is I want to turn this from polar into a Cartesian equation. Okay. And so to do that, I think the easiest way is to take the cosine term and to write that as x over r, or equivalently, you could just multiply both sides by 1 plus e cosine theta. You get ed on the right. And this is going to be r plus e times r cosine theta. And r cosine theta is just x. So this is r plus ex equals ed. And then what I want to do is I want to move the x term over because r is going to be kind of an ugly expression, but r squared is nice. And so to square both sides, I'm going to solve for r. And therefore, r squared is going to be this left term squared. So that's going to be, I might as well just write it all out completely. This is e squared d squared minus 2e squared dx plus e squared x squared. And r squared is, of course, x squared plus y squared. Okay, and so we end up with x squared plus y squared equals e squared d squared minus 2e squared dx plus e squared x. And then I want to do a few things just to kind of turn this back into something that we can look at, something that we know about. If I take the e squared x term and move it over to the left, we get x squared minus e squared x squared. And in other words, what ends up happening is when I move this over, we end up with 1 minus e squared times x squared plus y squared. And then we can also add the other terms over. And I'm going to leave the e squared d squared term on the right, okay, just so that it's consistent with what I have up here. It's for no other reason than just style here. And let's think about what's going to happen for the various values that we've talked about. Okay, so first of all, if e is equal to 0, the right way to think about this is that if e is 0, then d is infinity. And it's a little bit strange to talk about it in these terms, although that kind of makes sense when you think about 0 times infinity being indeterminate, and that can be any constant. You know, we know we're kind of making circles more complicated than they need to be, which is a little bit silly, but we know that circles are all going to look like something like r equals c, right? Because you just have the radius as some fixed constant, and then that's the polar equation for the circle. So again, circles are a little bit strange here, but if e is a number between 0 and 1, say a half, then think about what's going to happen with 1 minus e squared. So if e is something like a half, then this expression, 1 minus e squared, is going to be positive. And if this is positive and the y squared term is positive, then you end up with the ellipse, just like we talked about before, right? So if a and c have the same sign, if they're both positive or both negative, then you get an ellipse. And here the y squared term is positive just because we were working with one particular expression. But anyway, so if e is between 0 and 1, you really do get an ellipse because 1 minus e squared is positive. And if e is equal to 1, then you really do get a parabola, because if e is equal to 1, then this x squared term is gone, and you end up with something like x equals y squared with constants. It might be a shifted parabola, who cares, but it's a parabola. And if e is bigger than 1, if e is like 2 or 3 or 5 or something, then 1 minus e squared is going to be negative, and then your x squared and y squared terms are going to have opposite signs, and you get a hyperbola. Okay, and so this really does not just convince us that these types of expressions are conic sections, but it actually tells us why these work the way they do. So again, when e is less than 1, you get an ellipse. When e is equal to 1, you get a parabola. And when e is greater than 1, you get a hyperbola. The last thing that I want to talk about is if you're given just a general expression like this, how can you graph this? How can you figure out exactly what's going on here? And so what I want to do is I want to look at the expression r equals 4 over 3 plus cosine theta. And what I want to do is I want to figure out, is this going to be an ellipse, a parabola, a hyperbola, or what? And I'll come back and I'll kind of at the very end explain how I knew ahead of time without doing any calculation what's going to happen. It's obvious to me that this is an ellipse, and I'll explain why. But what I want to do first is I want to show you how can you algebraically do this. And so kind of the trick here is you're going to take the denominator and you're going to factor out that first term so that you end up with a 1 plus e cosine theta. In our case, if we factor out a 3, we get a 1 plus 1/3 cosine theta. And we have a 4 up top. In fact, if we want, we could write this, we can move this 3 up and we could make it a 4/3 up top. And we know that our eccentricity is going to be E, because in general, the expression here is R is ED over 1 plus E cosine theta. And so now we need to think about what's D if E is 1/3. So we know E is 1/3. We know E times D is 4/3. And so that tells us that D is going to be whatever we have to multiply 1/3 by to get 4/3, so 4. So D is going to be 4. Okay, and that's really it. If D is 4, then our directrix is going to be x equals D. We have an eccentricity of 1/3, which is between 0 and 1. So that means that we have a parabola. And therefore, most of these are going to be kind of matching. But we're going to have a excuse me, what did I just say? If E is 1/3, we get an ellipse. I don't know what I said before, but we get an ellipse. And so this is going to turn out to be something like that. It's the worst ellipse I've ever drawn in my life. Actually, it's not, but that's okay. So we get an ellipse like that. We get the expression x equals 4. So that's our directrix. Okay, and then that's roughly what the graph is going to look like. Okay, just to go back in the last comment that I'll have in this video, we had 4/3 plus cosine theta, and ellipses are the only ones that are kind of finite shapes. What I mean is that they're really bounded. You can fit them inside some circle. Parabolas and hyperbolas go to infinity, and hyperbolas, have the same kind of infinite size, right? And so those go to infinity. And I know that this expression is not going to go to infinity because you're never dividing by 0. Cosine is between -1 and 1, and therefore 3 plus cosine theta is between 2 and 4. But in particular, it's never 0. And so that's how you can tell right away that this is going to be an ellipse, is that the denominator is never 0. So that means that the curve is always defined and nothing ever goes to infinity. If this, on the other hand, was something like R equals 3 plus 4 cosine theta, now it's possible for the denominator to go to infinity. And so this is going to turn out to be either a parabola or a hyperbola. Turns out actually it's a hyperbola because of the mismatch of the coefficients 3 and 4 here. So this would turn out to be a hyperbola. But there's these kind of few tricks that you can do. I think just for now, if you just kind of go through and systematically do this algebraically like I did here, where you factor out the number, that gives you the eccentricity, and then you can just plug it in. It's a very basic algebra equation there. That'll give you the directrix. Okay, so I think that's the way to go for now.